This is question 5 from Module 4, January 2008. And again, we're starting here by determining what we understand by the term field. And remember, field is the region in which a force is experienced, or the region in which an object experiences a force. So it's the region in which an object experiences a force. We have a table now which compares gravitational and electric fields. So the physical quantity responsible in a gravitational field is mass, and an electric field obviously is charge. Force is attractive, okay, and that's attractive or repulsive. So you can have an attractive field. The electric field is measured in newtons per coulomb. The field strength here, the unit for that is newtons per kilogram, or meters seconds to minus 2 is an equivalent unit, but newtons per kilogram is the one that I would favour there. We now have the nucleus of a lithium atom, 3 protons, considered to exist at the corners of an equilateral triangle as shown. The length of the triangle is 2.4 times 10 to the minus 15 meters. And we're asked first of all just to calculate the magnitude of the electrical force that Q exerts on P. So we're looking at Q and P. So these are 2 charges, okay? They're 2 protons, so they're going to have an electronic charge. That's 1.6 times 10 to the minus 19. So remember, the charge on this is 1.6 times 10 to the minus 19 coulombs, because it's a proton, it's a positive charge of that. So the magnitude of the electrical force, we're going to use F is equal to K times Q1 Q2 over R squared. That's Coulomb's law, the formula for Coulomb's law. So we now have 9 times 10 to the power of 9 for K times 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19 again. And we're dividing that by their separation squared, so that's 2.4 times 10 to the minus 15 all squared. Put that into your calculator and calculate that out, and we get 40. So the force is equal to 40 newtons. Right, on figure 5.1, draw an arrow to show the direction of the resultant electrical force acting on proton P as a result of protons Q and R. Right, so here's proton P, proton Q, and proton R. So I'm just going to go across the side here so we can see what's happening. So there's P, R, and Q. And what's happening is we get a force. This is P here, so that's the force due to Q, and we also get a force due to R. The combined effect of them then is that plus that to give that. And so what happens is that's the resultant force. So that's the resultant electrical force. It acts directly up the page. Then calculate the magnitude of the total electrical force acting on proton P. Right, well, the total electrical force acting on P, we need to go back to this diagram here again, so that if I redraw that down here, we have the force due to Q, and we have the force due to R. And we just worked out that that's equal to 40 newtons, and this one is also equal to 40 newtons. What we need to know now then is, what's the angle? Well, that angle is 30 degrees, and so we have the force, the resultant force is 40 cosine 30 due to Q, and 40 cosine 30 due to R. Horizontally they're going to cancel each other out, so we've just got that one going up, so it's 2 times 40 cosine 30 that gives a value of 69 newtons. Alright, so we now have a point charge, and we've got a set of axes showing the field strength and how the field strength varies with distance from the source. And well, we should know that E is equal to, for point charge, so E is equal to K times Q over R squared. So E is proportional to 1 over R squared, so it's an inverse square relationship, so that should be coming like so. We then have two parallel plates with the constant potential differences maintained. Sketch the graph of field strength magnitude against distance from the negative plate. Okay, and this is where we need to be careful, because this is a uniform field, so the field is the same all the way across there, which means that as we move across from there, what we get is a horizontal line. Okay, in this one here we've got inverse square relationship from a point source, and we've got that. If we were to remember the field, what it looks like from there, those are going out because it's a positive charge, and that's the direction that a positive charge would move as a result of that. Here from across from there, so we've got a series of equally spaced parallel, okay, straight they should be, which is why you should use a ruler, and around the edges it bends a wee bit, but the uniform field in here giving us a field strength which looks like that. And that's the end of that question.